Sustain-TEX, the new road to a sustainable economic strategy in the textile sector, MOOC 4, Recycling, Waste Management, and Energy Transition.
Unit 4.1, Introduction to the Textile Industrial Waste Management. Author, textiles.cat. This is the table of content. 1. Introduction. Where is the problem? The current textile value chain is full of inefficiencies and wastings in terms of resources, water, energy, etc., and waste. Resources are often discarded prematurely, becoming industrial waste. The environmental impact of this waste, together with the consumption of water and energy, is massive. Many materials and products become waste during the manufacturing process. Traditional linear economic models contribute to this growing problem. 2. The linear economy versus the circular economy. Shifting paradigms from linear to circular. The linear economy follows a take, make, dispose approach, where resources are extracted, used to produce goods, and discarded as waste without significant recycling or reuse. The circular economy aims to minimize waste and maximize resource usage, implementing several approaches: reducing waste generation at the source, reintroducing industrial waste back into the value chain, promoting the effective use of material resources, designing products for longer use, reuse, and recycling, or eco-design, fostering collaboration and synergies between industries, industrial symbiosis. 3. Fundamental concepts. Beyond the circular and linear economy main concept, some related and at the same time crucial elements must be mentioned. Industrial symbiosis, a business strategy that promotes collaboration and synergies between companies to improve resource efficiency. Eco-design, a methodology for integrating environmental criteria into product design to improve their environmental impact throughout their life cycle. Life cycle analysis, LCA, a methodology to evaluate the environmental impact associated with a product, process, or activity throughout its entire life cycle. Informed substitution, replacing hazardous substances with safer alternatives, evaluating risks and viability. 4. Impact of recycling and waste management. Fibers. Recycling. The use of recycled fibers reduces dependence on virgin raw materials and the environmental impacts associated with their production. No recycling. The production of virgin fibers, especially synthetic ones, involves high consumption of energy and resources and the release of polluting substances. The production of PET is almost twice as high as that of cotton and 7 times higher than that of wool. Waste management. Recycling post-consumer and industrial textile waste is essential to prevent it from ending up in landfills and to reintroduce it into the value chain. It is key to detect which resources are not used and end up as waste in order to reintroduce them as raw materials. 4. Impact of recycling and waste management. Spinning. Recycling. Leftover polypropylene threads can be reused to obtain recycled granules, which can be used in the packaging industry. No recycling. The generation of thread waste during spinning can be considerable if not managed properly. Waste management. The transformation of polypropylene thread waste into recycled granules reduces the amount of waste and offers a new raw material. 4. Impact of recycling and waste management. Woven and non-woven fabrics. Recycling. Recycled fabrics can be used to manufacture new products such as bags or blankets for babies. Companies like CP Aluart use recycled polyester from post-consumer PET bottles to create working indumentary. No recycling. The generation of fabric waste during production, such as scraps and defects, implies the loss of resources and the accumulation of waste. Waste management. The reintroduction of fabric scraps into the production process as raw material for filling cushions or for the manufacture of new products. There are examples of reusable bags made from fabric scraps. The substitution of resins by thermobonding fibers in the production of non-woven fabrics facilitates the recycling of the material as it becomes a monomaterial product of polyester. 4. Impact of recycling and waste management. Manufacturing process. Recycling. Leftover textile material can be recovered to reintroduce it into the production process. Companies like Pont, Enroll, and Armingle recover the edges of non-woven fabrics to reuse them. No recycling. The high consumption of energy and water during manufacturing and the generation of waste have a negative environmental impact if sustainable practices are not implemented. Waste management. The implementation of processes that reduce the consumption of energy and water, as well as the reuse of leftover materials, reduces the environmental impact. 4. Impact of recycling and waste management. Finishing. Recycling is not directly applicable in this phase, but the substitution of hazardous chemical products with more sustainable alternatives is key to reducing the environmental impact. No recycling. The use of hazardous chemical products and finishes can cause health problems and environmental pollution. Waste management. The substitution of fluorinated compounds by alternatives such as silicones, paraffins, and dendrimers, as well as the use of phosphorus-based products instead of brominated ones, are examples of improvements in waste management.
5. Challenges and opportunities in each phase. Fibers. The traceability of recycled materials, the quality of recycled fibers, and the availability of recycled raw materials are the main challenges that the materials sphere shall tackle to ensure the implementation of circular economy and eco-design in the textile value chain's first phase. Spinning. The need for technologies for the separation of fibers and the transformation of thread waste into new products and the capacity to implement this process would facilitate the recycle and reuse initiatives. Woven and non-woven fabrics. The difficulty in recycling mixed fabrics or fabrics with chemical finishes. Most of the fabrics are different to each other, having suffered several and variated treatments that prevent them to be mixed in a posterior uniform fabric. Improvements in traceability would facilitate this task. Manufacturing process. The high investment in new technologies, the optimization of energy and water consumption, and the management of generated waste will definitely ease the implementation of circularity in the textile value chain. Finishes. The substitution of hazardous substances with safer alternatives, the need for more information about alternatives, and the guarantee of the quality and properties of the new products. 6. Success stories and best practices. Etisilk. Manufacturing blankets for babies with textile waste. Radici Group. Production of a monomaterial ski suit in polyamide. Tintoria di Quarren. Natural herb dyeing process. Bonditex. Replacement of melamines with isocyanates and use of fluorine-free products. Texkina. Use of infinifiber that reduces environmental impact. Musa, Dye Care TM innovation for sustainable dyeing. Textina, use of infinifiber that reduces environmental impact. 6. Success stories and best practices. Simpasa, return of yarn cones and application of energy efficiency measures. CP Aluart, donation of discarded pieces to NGOs and use of recycled fabric. Etisilk, Polysilk, creation of new products with textile waste. Hydrocolor, development of biodegradable products. Hilaturas Arnau,
use of natural and sustainable fibers. Liasa, use of regenerated cotton and production of reusable masks with recycled polyester. Arpe, use of recycled polyester for masks and use of surplus material for pillows. Mitsa, reuse of surplus material for packaging. Pont Aurel Yarmengol, replacement of resins with fibers and recovery of surplus material.
7. Conclusions. Effective industrial textile waste management necessitates a transition from a linear take, make, dispose model to a regenerative circular economy that prioritizes keeping materials in use and minimizing waste. Collaboration and the establishment of industrial symbiosis between different sectors, such as packaging and textiles, are crucial for creating valuable synergies where one industry's waste becomes another's resource, leading to reduced waste and cost savings. The integration of eco-design principles and life cycle assessment methodologies is essential for designing textile products with reduced environmental impact throughout their entire life cycle, from raw material sourcing to end-of-life management. Addressing the use of hazardous chemicals in textile finishing and promoting their substitution with safer and more sustainable alternatives is vital for protecting human health and the environment, as highlighted by regulations. Despite existing challenges, there are real-world examples of circular economy applications within the textile industry, including the use of recycled materials, upcycling of waste, and inter-industry collaborations, demonstrating the technical and economic viability of more sustainable waste management practices. These are the references used to extract the information from this unit. Thank you for your attention.